All right, we're going to try to accomplish a couple of different things with this video. Um, the first is we're going to go through one more time how we do the process of solving or finding the x-intercepts of a quadratic from the standard form. X-intercepts also sometimes called zeros, sometimes called roots. They're kind of depending on how the way things are set up. This is an important concept, so it ends up having multiple ways of referring to it. Now, the second thing I'm going to try to accomplish is that this process is fairly repetitive in the way that we do it, and you should recognize all the steps along the way. And so sometime a long time ago, somebody decided, this is repetitive enough that maybe I could generalize this and skip from the very beginning of the process to the very end of the process. This is going to end up being a little bit longer video because I don't want to rush things too much. So what I'm going to demonstrate is a process called generalization. It can be done a couple of different ways. One way to do it is just to replace all the numbers with A, B, and C and keep track of things that way. And we certainly could do that, and I've done that on another video, and I'll share that link with you as well. The other way is to choose what I call unusual values for the values of A, B, and C. So I've chosen a 7, a 13, and 11 that don't seem to have these kind of special properties like zeros and ones and twos tend to have. Okay. So we're going to do this, and when it asks me to multiply things together, I'm going to show them multiplied together, but not actually multiply them together, just so that maybe at the end I can see what has happened to these three numbers that lead me to the answer at the end. All right, so let's go ahead and get going. The first step of the process here, if I'm going to try to find the x-intercepts always happen when the output is 0. So I'm going to take my equation here and set the output to 0. The process then was to get this into its vertex form and use an arrow diagram to solve from there. So first step in getting in the vertex form is to get that 7 out of the way, which is going to leave us an x squared plus 13 over 7x, and then we'll kick this plus 11 out to the end and equal to 0. And we did that because we wanted to build a square with an x squared right there. And then we're going to keep these parentheses and keep the 7 that is out in front and the plus 11 equals 0 going on out here. But inside here now, this 13/7 x, half of that has to go in each of these boxes. So I'm going to write that as half of 13/7 x is going to go there, and half of 13/7 x is going to go there. And so on this, I know that this has to be an x and that's an x, and then this would have to be a plus 1/2 times 13 over 7, and this is also a plus 1/2 times 13 over 7. And so the area of this square, in order to complete this square, I'm going to multiply those things together. So I'm going to have a 1 over 2 squared times a 13 squared over 7 squared. This is the part where I said I'm not really going to multiply them together. I'm going to show them multiplied together, but not combine this into a single number. And of course, that little green square right there is something new to the problem that wasn't there before, and I can't do that or it will fundamentally change the problem, so I also have to subtract a 1 over 2 squared times 13 squared over 7 squared, so that these things together make a 0, and everything else that I have matches everything that was on the line above it. Okay, the next step in the process then, we still have the 7 here, but now I'm going to rewrite the area of this square. I'll redo that in red here. So I'm going to write the area of that square as a length times width. which is an x plus 1/2 times 13 over 7 quantity squared. That covers the 4 pieces that are inside that square. I still have this minus 1 over 2 squared times 13 squared over 7 squared hanging out here. Let's see, green parentheses there, plus 11 equals 0. So this says exactly the same thing as every line above it. All right. And this now, the only thing left to do is distribute that 7. So this is going to leave me with a 7 times x plus 1/2 times 13 over 7 squared minus 7 over 2 squared times 13 squared over 7 squared. So I multiplied the 7 times the 1 that was above the 2 squared. And then I still have the plus 11. And that's equal to 0 right there. And those last two are just constants, so I'm going to work on combining those together. I still have the 7 times x plus 1/2 times 13 over 7 squared minus 7 times 13 squared over 2 squared times 7 squared plus 11, and if I'm going to combine those, I'm going to need the common denominator of 2 squared times 7 squared. So I'll multiply by 2 squared times 7 squared over 2 squared times 7 squared, showing all my steps here. So now I got 7 times x plus 1/2 times 13 over 7 squared. And with the common denominator here, I've got a 7 minus 7. I'm going to change that to a plus negative 7 times 13 squared plus 11 times 2 squared times 7 squared, all over 2 squared times 7 squared. Looks like a mess right now, but this is, and all these things again, we're still equal to 0. This now is my vertex form though. So if I want to solve and find what makes this thing equal to 0, I start with the x, and the first thing that's happening here with the x, I can see right here, is that I'm adding 1/2 times 13 over 7. Okay. And then I get my parent function. That 1/2 or x plus 1/2 times 13 over 7 is getting squared. And then the next thing here is the multiplication by 7 out in front. And then finally I add this other massive piece on here. So I'm going to add on there a negative 7 times 13 squared plus 11 times 2 squared times 7 squared over 2 squared times 7 squared. And I want that to all at the end equal 0. So I'm going to get back to my x, which means I need arrows that come back the other direction. This is going to be subtracting then the negative 7 times 13 squared plus 11 times 2 squared times 7 squared over 2 squared times 7 squared. This is going to be dividing by 7. The opposite of my squaring, my inverse operation there, is a plus or minus square root. And then I will finally subtract 1/2 times 13 over 7. Okay. Or 13 over 2 times 7. I may end up writing it that way at the end. So first step following the arrows in, 0 minus that, okay, is going to leave me a negative of that. If I distribute the negative through there, I'm going to get 7 times 13 squared minus 11 times 2 squared times 7 squared, all over 2 squared times 7 squared. And then on my next step, I'm going to divide that by 7. Well, I've noticed that I've got a 7 here and I've got a 7 in this part, and if I'm dividing this whole thing by 7, which is the same thing as multiplying by 1/7, then this 7 can cancel that out and cancel one of those out. So that's just going to leave me with a 13 squared minus 11 times 2 squared times 7 over 2 squared times 7 squared. And that I am then going to, on my next step, do a plus or minus square root of that. Okay. When I do that, everything in the denominator right now is squared anyway, so that makes that nice. That becomes a plus or minus, nothing nice in the numerator there, square root of 13 squared minus 11 times 2 squared times 7. All over now just a 2 times the 7 because I did the square roots of both of those, and then in my last step I'm going to subtract. I'll do that out in front. Adding a negative is the same as subtracting. So this is a 1 times 13 over 2 times 7, and I find that these are my answers. Okay, they happen to both have the same denominator, so I can write this as 13 plus or minus, or let's see, this was negative out here. So negative 13 plus or minus the square root of 13 squared minus 11 times 2 squared times 7 all over 2 times 7. That's two different answers, one when I add, once when I subtract. Now, let me go up. I'm going to grab a copy of my original problem. Clone that and throw that down to where we are. So here we are in the original problem. And if I start comparing the numbers in here, I see the 7 was where, in the standard form, what I refer to as B. The 13, or A, 7 is A, the 13 is the B, and the 11 is the C. And I can see all of those numbers in here. So if I was going to try to generalize this process, now everywhere I see a 13, I'm going to put a B. So this is negative of whatever B is, plus or minus the square root. There's my 13 again, and it's being squared. Here I've got minus 11, which is the C. The 2 was never really a part of the original problem, so I remember that came in there because I had to split the B in half and then make that square. So that looks like it's always going to be a 4 no matter what. And this is the A. And it is all over, there's the 2 again, that didn't come from this problem, it came from the process, times the A. Okay. All right, cleaning that up a little bit, the C times 4 times A, I wouldn't normally write things like that, so I'm going to go with the opposite here of whatever the B was, like it said, plus or minus the square root of the B squared minus, numbers first, then I'll go alphabetical order on the others, all over 2 times A. Okay. What this is a generalization of the process. This will allow us to go all the way from the original question of here's a standard form and I want to know what the x-intercepts are. In one step here now, I have completed the square, made the arrow diagram, put the 0 at the end, went backwards on the arrow diagram to get to this. So this now, if I just have my standard form equal to 0, because I'm trying to find the x-intercepts, and I grab the coefficients from the standard form, what the A, the B, and the C are, and I put them into this equation, that should take me directly to the answer without having to do all of the completing the square. Okay? This was done a very, very long time ago. It's very, very well known. It is called the quadratic formula. And this is a way, a shortcut, if you will, to find the x-intercepts when the equation that you have is in standard form.